Hi, this is Terry Dennery of the MathWorks. Um, so this video is going to be called something along the lines of get it into Simulink and aren't MATLAB function blocks just awesome? All right, so anyways, hopefully that's descriptive enough of what we're going to do with this one, that is our main goal. Let's get it into Simulink and let's show the advantage of getting it into Simulink too. So this is where we arrived at the end of the previous video. I made a slight modification to simplify the calculation of what I really want. Okay, and it's the acceleration of the motor. And with that, I'll kind of comment some of these things out that I don't think are super necessary. Okay, and so that kind of simple example is I realize was kind of the point of this video as well. All right, and that there's something really awesome about having lines of code. Just having the direct access to the software. That it facilitates your ability to kind of make modifications that make it even more useful. And certainly, kind of it all being there, you can kind of look through and see, in a very explicit form, what this is. So, anyways, with regard to kind of operating at a code level, you're going to see me do a few things like what we just did here. And we're going to also kind of get into something that I thought was going to be too technical of a point. It may still be, but I think it's a critical point. And certainly if we don't address it, it'll be a little bit confusing why I'm doing what I'm doing. All right. And so, anyways, with that in mind, I want to address essentially there's a thing that I refer to as a singularity. Right. And if we look at our model as we have been working with it for the last couple of videos, it's a 4-bar linkage and everything. But what I want to get at is that this combination of bodies and joints, there's actually two expressions of this that ultimately represent two different types of mechanisms, right? And so the way I'm going to show that is, again, keep all my joints, keep all the lengths the same, but what I'm going to do is I'm going to split this one right here so that I can get to the other configuration. Again, so I'll use this little move tool, right? Maybe bring that guy like there. Let's bring this one like that. And let's now rejoin that joint. We'll choose that first option, which will move the bodies, right? And so that what I'm saying is there's your second configuration, right? And that the difference between the two, it's actually very efficiently expressed in the initial conditions for each of these additional revolute joints. And so I'm going to go into C ground, for example. And you'll see that in this second configuration, it's initialized with 76.4 degrees, right? And so just to kind of show the difference, I'll bring it back to where we were before. And in this configuration, you'll see that C ground is equal to 0, right? And in general, I define a nominal, I'll say, configuration or positioning for all of my mechanical assemblies. And I always, in nominal configuration, set my initial condition to 0. And for that reason, quite often, things I do using integrator blocks, the defaults of the initial condition being 0, it generally works for me. So anyways, as we go through this, I think you'll see why this is important and why the solution is going to be composed the way it is, right? And so now I just want to kind of get it into Simulink form. So again, oops, we're not there yet. So let's copy all this. Okay, let's get into the Simulink model right here, right? And I'll begin by even changing the name of this. So let's save as. Okay, and I'm going to use that name. So I practiced it earlier. And so the point of this model is to essentially show the equivalence of SimScape multibody and what we're going to create for MotionGenesis. Right, and as I mentioned, MATLAB functions are absolutely awesome. Right, and so let's go get one. And so I go to our Simulink browser, and there it is right there. And as I double click on it, it opens up inside the MATLAB editor, right? And the very simple default of, y is equal to a function of u, where it actually is y equals u. Well, we'll replace every bit of that with what we got from MotionGenesis, right? And so now I want to kind of get into the creation of the function statement that's going to really serve our needs. And so I want to take that motor acceleration that's calculated at the end here, and I want to replace it as my output, right? And now I want to kind of address what I'll call, well, let's just call them random selections that kind of reflect maybe there's a bit more for me to learn with regard to MotionGenesis, but lead to things that I do not want. But because I'm looking at it and I have access to the code, it's not a hard thing to work around, right? And that, one of them is that the angles of all these other revolute joints are being set to 0 within the function. Well, that is not at all what I want. I do not want them always equal to 0. And so we're going to make them inputs to the function, right? And in general, these 4 essentially represent the state, even if there's some redundancy between the 4. But they do represent the state of the system. And so we just put in to our input list. Let's just paste that in again, but this time we'll add this little dt notation that indicates the first derivative of the motor angle. And then let's get these other 2. All right. And this being reported is kind of getting into this idea of the 2 configurations of the 4-bar linkage. All right. And we'll say that me personally, as I first encountered this problem, I didn't think that I needed to even worry about the other 2 joints, but it's this thing that we got into with regard to configuration. Right, so that all looks pretty good, and again, I can compensate for whatever error I made that allowed these to show up with 0 assignments within the function by merely commenting it out. Another thing I want to comment out is that I'm going to send in all my angles in radians anyways, and so I don't need to convert them to radians. And if I attempted to, of course, it would be wrong. So let's not do that. And then finally, this thing that I must have done that set my torque always to 0 inside the function, I just want to fix that too. Right? And so that will be inputted. It'll be actually at the top of the list. And then this last piece is how we set it up so that initial condition can be set, right? And I'll just copy these in. Oops. And I'll just add again the notation of dt. Okay, and notice how these show up in blue. That means it's essentially the highlighted term or variable. And so as I go down into the code, oops, I'll see even where it is defined. And so it is calculated within this code, and you're going to see it's going to be based mostly on what the motor angular velocity is, right? But I think we kind of got it now, and so now we're going to kind of get to the fun part. We'll get back to the Simulink model. Oops, I kind of messed up. I like in practice I was kind of showing that in a way where you saw it get morphed, but basically by hitting save, it reconfigured the block so that it matches my function statement. So my inputs are defined by that function statement as well as my outputs. And what we have here essentially is a calculation of, I'll call it the state derivative. Okay, and that the state is input into it as well as the torque, and so we need to update the state. And Simulink's awesome at that too, because it's got integrator blocks. So let's just go up to, we'll use the continuous ones as opposed to the discrete ones, but let's go to continuous. And our motor angle, is kind of operating at the acceleration level, so second order integration is required there. And so this block is super efficient at kind of doing both the first and second order integration, and so it's a good idea to use it. Let's say I want to just confirm dx goes into dt and x goes into the angle itself. right? And so here's kind of the point that I was kind of getting at with the multiple configurations. By using an integration block, it's very easy to set that initial condition right there, right? And again, my nominal configurations are always 0 for initial condition. Right? So I'll bring that in like that. I'll, oops, paste. I'll bring that in like that. And just kind of move it all over here. Let's drive it with something. And so I'm good with this. Turns out, the 1 Newton-meter is actually quite a bit of torque for a linkage the size of what we're looking at. And so then let's just kind of compare the results. It's not with a C, but with an SC scope. All right, and here we're going to be operating with a bus, so BU usually gets me to bus selector pretty quickly. And again, knowing this import, I know that it's going to make available to me speed and, oops, show that speed. So I selected that. Let's remove those. And we'll push that into that block. Let's move it over here. And speed is the dx calculation right there. Right? So we'll compare the two. All right. And assuming I did everything right, this should work pretty well. Right? So there's our animation. It's provided by Simscape Multibody. Why it's a really good idea to use Simscape Multibody as well. But we'll see in a moment is that we're going to get a real good speed advantage through what we just did in importing that MATLAB function. Especially if we, and we'll look at the scope, and that's precisely what I wanted to see. All right, and whenever I just see blue, and I know that there are two signals, I know that the two signals are comparing exceptionally well. All right. And I want you to notice that the speed, especially as it really gets cranked up to very high values of speed, this is radians, so it's kind of spinning at like 2,000 radians per second right now. So that's really, really fast. So anyways, let's go ahead and click on OK. And because it's going through so many oscillations so fast, you can't really distinguish it. And so it's good to use these scope zoom tools. And this is what I'd call a time zoom. And so I've essentially narrowed what we're looking at to, what is that, like 100th of a second from here to here. And you'll see, I think it's at least 2 oscillations. So we must be spinning at about 200 RPM, not RPM, 200 RPS right now. And again, at this fine, resolution in time, we're seeing blue and yellow are absolutely right on top of each other. So I'm very happy with that validation, right? And then finally, we saw how it slowed down tremendously at the end. I want to just kind of run this piece of it. And so the way we'll do that is we will take all this and we'll merely comment it out. Okay. So this time the calculations can be based purely on what we did with MotionGenesis. Well, let me be more precise. It's all done with Simulink, but it's that function as calculated, or at least formulated by MotionGenesis. And we're going to see that this whole thing is running probably like 5 times real time. So the speed improvement, I think, is quite clear, and that's a really helpful thing, right? And so anyways, thank you. Okay, bye.